particle physics. It is at the forefront of modern science. It is one of our best descriptions of the world and already has many practical applications, such as in cancer therapy. But when we tried to learn it, there was one small problem.
It's really, really difficult.
It's abstract.
Like, what is all this new terminology? Leptons, fermions?
We didn't understand any of it.
Take a look at this video.
What even is that?
Did you understand any of that? Because when we first looked at it, we didn't understand any of it either.
But what if I told you we went from not understanding anything in that video to designing an experiment where we bend particle beams using crystals?
So, from November to March, we participated in a physics competition called Beamline for Schools. So, Beamline for Schools is a competition where we design a physics experiment to be performed at CERN, DESY, and ELSA, the biggest particle accelerators in the world. The competition challenged us to design an experiment based on their subatomic particle beams, which includes protons, electrons, which are the very building blocks of our universe.
But we signed up not knowing a single thing about particle physics. The scope of the field was so broad and complex that our first attempts at research left us dumbfounded.
It was really demotivating because we didn't know where to start and how to start.
But then it hit us. Why are we treating particle physics like something completely new when it's just a more complex topic in physics? So we decided to start applying skills we had already learned in school, and soon everything started to fall into place. Today, we would like to share with you our experience in learning particle physics, show you the three skills that aided us in our learning, and hopefully encourage you to also take a dive into particle physics or any other complex area in science.
So, the first skill is learning through modeling. So, at school, whenever we have to learn something really complicated, we use models and analogies to help us understand. So, for example, in biology, we think of the plant stem as a straw. And in chemistry, we think of the electrons in an atom as planets orbiting the sun.
Just like at school, we can also use models and analogies to help us understand concepts in particle physics. For our experiment, to help us understand how particle beams are bent using crystals, we use this model shown on the screen.
As you can see, particles are represented by very tiny circles, and the crystal itself is represented by layers of atoms. When the particles approach the crystal, they sometimes get trapped between these layers, which results in a process known as beam channeling. When beam channeling occurs, we are able to bend the crystals and deflect the particles in a certain direction.
We can also think of it as a skateboarder skating on a sloped surface. The sloped surface guides the direction of the skateboarder, just like how the crystal lattice guides the direction of the particles. Before doing an experiment, it's important that we have a good estimate of what the results will look like.
So we are able to do the calculations ourselves, but there's just one small problem. It's really tedious and difficult. And that's where computer simulations come in.
Computer simulations may sound complex, but everyone can do it. If you've used something like a PhET simulation before, you've already taken the first step. For example, at school, we might have used PhET simulations for electrical circuits to help us predict currents and voltages.
Except that in particle physics, we use something called GNT4. So GNT4 is a Monte Carlo simulation, which relies on vast databases to make very accurate predictions. It's the gold standard in particle physics, meaning actual particle physicists use it to make predictions. In our experiment, by relying on our coding experts, we were able to create a very accurate simulation of an experiment, which produced very reliable results that could be used to test our hypothesis.
On the screen, you can see a gene-force simulation of the famous Rutherford gold foil experiment. You can see how some particles are deflected away at large angles, showing how atoms have a small, dense nucleus.
Finally, whenever we need help or have a request at school, what do? We obviously talk to teachers.
Similarly, we also had a request. We needed a very specific piece of lab equipment, a bent crystal, produced only by a few research institutions around the world. At first, we thought it would be impossible to find one, but then we realized we can just ask researchers and professors. So we decided to contact these experts in the field, and against all expectations, one professor not only offered us a bent crystal, but even gave us advice on how to properly integrate it into our experiment.
That was a huge revelation for us because in the past, we used to think of professors as unapproachable, distant, too busy to care about some random high schooler's physics experiment. But once we actually took that first step, wrote the email, and sent it, we realized something really, really important. And it's that until you actually take that first step, you don't know what's going to happen. And that's the third skill. We all know how to do it. We just have to know when to apply it. So, after listening to that talk, who wants to do their own particle physics experiment? Yeah, maybe not a lot of people, but hopefully you could also have some takeaways just like we did after listening to the talk.
So, what did we realize?
We realized that learning particle physics actually isn't that different from learning any other complex science at school.
Exactly. We don't necessarily need advanced knowledge to start learning particle physics. All we have to do is apply familiar skills in an unfamiliar context. Firstly, we make the ideas understandable using models and analogies.
Second, we make computer simulations, even if it's just with simple softwares at first.
And finally, we ask for help to refine our ideas and move forward,
And that's how we went from knowing nothing.
posing a real experiment.
Obviously, we're just still scratching the surface because there's a lot of issues when it comes to practicality and theoretical rigor.
But we've already taken the first step, and so can you, because we all have the skills to begin.
Thank
Thank
you.
you.